So hi, we're group 4, and we worked on privacy-preserving detection of depression and suicidal intent from speech data. Depression is a serious public health concern. In the US, it is estimated that 1 in every 4 adults have depression. Depression can be life-threatening, in the worst cases leading to self-harm or even suicide. The good news is that depression is highly treatable. However, due to societal stigma, denial, and other factors, individuals are often reluctant to report when they experience depression or suicidal symptoms. In fact, only half of Americans who experience major or long-term depressive episodes receive treatment. Additionally, even for those who do receive help, it is often difficult for patients and medical practitioners alike to assess treatment effectiveness, both because they rely again on self-reporting and because they are only able to examine behavior during infrequent consultation appointments rather than other points in the patient's lives. There has been prior work to solve this issue. A team of CS researchers and psychologists at the University of Michigan has proposed analyzing speech data to detect depression and suicidal symptoms. Specifically, they demonstrate the effectiveness of using machine learning on phone call speech data to make an evaluation of the status of patient mental health. The problem is this type of analysis necessarily requires large amounts of privacy-sensitive patient data, both in the form of private phone conversation information as well as the outcome of the model analysis. The state-of-the-art does not adequately protect the privacy of this patient data, as it evaluates patient information in plain text form. We propose using Microsoft Seal to get better privacy guarantees when using this system. This is an example scenario of how we envision using Seal to protect patient privacy. A phone would first send record patient conversations, perform feature extraction and feature encryption, and homomorphically encrypt the feature vector using Microsoft Seal. The phone would then send this data to a server in the cloud, which would apply a machine learning model to the features, resulting in a homomorphically encrypted output of symptom information. This symptom information is then sent back to the phone for further analysis. We envision that the phone may notify patients when they might benefit from seeking additional help, empowering patients to have a better understanding of their mental health. In the worst case, it may even be able to pop up suicide prevention resources if suicidal intent is found. In the second scenario, we assume the patient is now receiving some sort of treatment plan. Treatment plans are typically not immediately effective, and there is not a one-size-fits-all approach for creating plans. Therefore, it is valuable to monitor the symptom changes over time to see whether a patient treatment plan works or needs changing. We imagine the user phone may display a chart of changing symptom patterns over time as shown. Here, rather than only relying on unreliable patient reports and infrequent clinical visits, patients and practitioners can now have a more comprehensive and objective evaluation of treatment effectiveness. Now Daniel will discuss further details of our approach.
Okay, thank you. So I'm going to go into a little bit more detail about the specific machine learning approaches. So we are relying on this previous work by this group of computer scientists and psychologists at Michigan, and they're using a machine learning approach that's called MAD-Dog for short, and it consists of 3 phases. So first of all, we do feature extraction on the speech data, so essentially segment the recorded phone call into different frames and extract some speech features from that, including, for example, pitch, the energy of your speech, or pauses between words. Then we take these different features and run dense neural networks that are pre-trained to classify and predict emotions. In particular, we focus on these 5 emotions: guilt, worry, hopelessness, anger at others, and anger at self, which have shown to be highly predictive emotions in terms of depression and suicidal intent. And this dense neural networks then output an emotion score for each of these emotions. The third and final step is then to take these emotion scores and perform analysis on their standard deviation. And the result of this research paper was essentially that healthy people that do not have depression or suicidal intent have a larger standard deviation in their emotion scores over time than people with depression or suicidal intent. So that is the predictor of this of depression or suicidal intent. The specifics of these dense neural networks are as follows. So they are very detailed in the paper and show that they have dense neural networks with 4 fully connected hidden layers. And they're using a randomized leaky value function for training of those hidden layers with a final sigmoid function at the output layer. And these dense neural networks are trained on a specific data set, which is coming from both healthy control subjects and patients that are undergoing treatment and also confirmed cases with suicidal attempts. And this data set includes 400 plus hours of phone calls. Going into the performance in SEAL, so we started the prototype implementation, and we're using, of course, dummy data for both the machine learning model and other stuff, but we still had some bugs, and we finally got estimation of the runtime a few hours ago. So we estimate that the naive implementation would take in the order of about 10 minutes for one run of this neural network evaluation. One step we had to think about was an approximation of these activation functions. And we chose 2 approaches for our benchmarks. One was that we approximated this randomized leaky value function with an approach that essentially reduces it to a degree 2 polynomial. And then where the parameters A and B are also learned during training. And then for the sigmoid function, we actually just used a simple second-degree Taylor expansion as a first benchmark of this prototype implementation. The detailed effects on the accuracy of the model with these changes is something that has to be explored further. The total depth of this computation is 11, and with a scaling factor of 40, we can choose these parameters and still have a few more levels of depth that we could add before we reach the security recommendations. The ciphertext at these parameters are about 5 megabytes, but we can fit 32 different conversation and neural network evaluations into one ciphertext if we pack it together. Some more extensions and future work that we are thinking about is that you could also use the system to assist practitioners during their evaluation of the patients in their office, and where you could also augment the analysis of the speech data with further video data, heart rate data, or something else, which is easier to do in a controlled setting. Then we also thinking about including non-phone call speech. So this app on your phone would just essentially replace your phone app and record these conversations automatically. But you could also think about a Bluetooth device that is essentially placed somewhere near your face and records your speech patterns throughout the day to give you a lot more data to work with. And then you could also generalize this approach to the identification of other disorders and general mental health well-being. Okay, thank you for your attention, and we are free for questions.
Sure. So why exactly were the parameters so large?
So these are the parameters we got to when we had a depth of 11 and we took the scale to be 40. So it may be that this scaling factor of 2 to the 40 is too large for this approach, but I think that's something we could change. It just missed the threshold of the previous parameters.
Okay. Anyway, okay, so that's great. But my main concern would be that the idea is sort of great, I think, but how well does the suicide prediction model work?
So in the original study, they showed that for predicting on their data set, they had an area under the curve of about 0.8, which is essentially classified as good from what I've gathered.
I see. I wonder if this is like a really narrow data set, what one ethnicity, for example, of people, or what kind. I mean, it's so difficult to find, especially for suicide risk prediction. Like, it's really hard to find the positive cases.
Yeah,
right?
so this data set is actually from this year. It was presented in September. So it's actually quite recent, and one of the first data set that includes a larger amount of people. And even there, the amount of people is only 40. Yeah.
So also regarding, you suggested that we could add, it would be possible to add other features, other medically relevant features to this, but then it makes it even more difficult to learn it. So I guess my main concern with this is the feasibility of the model learning itself.
Yeah, so I also think that this is cutting edge research on the machine learning side, and trying to get this intersection of psychologists and computer scientists to be more, essentially improve these approaches further and further. Because this, from their paper, they also say that these prediction methods have not really improved much above chance in the last 50 years.
So just a clarification, I didn't quite understand why you listed, I think it was like 1 trillion neurons. If you're taking speech data...
sorry, that should be commas, so for the different layers. Sorry, that's a little bit...
Okay, so, but like roughly how many features, for example, does the speech data have? Like the featurization, what are you using?
Yeah, so... Was it 128? Yeah, so...
I think the paper said it was 128, but I don't...
Oh, so a very small number of features of the speech.
Yeah.
Excellent, okay, thanks.
But the feature extraction step is actually quite... also uses a pre-trained convolutional neural network, a smaller one, but for feature extraction, yes.
I have one question and one comment. So the model is not very large, and I don't think it contains any sensitive information. So why don't you just download it to the edge device and just evaluate?
Yes, so why don't we have the model on the edge device? So there's a few reasons for this. The first is that our phones were concerned about efficiency and power, and so those are very important. And the other thing is that the models may themselves be private, so we wouldn't want to have the patients have access to those. And then I think we were discussing about this yesterday, that it's typically difficult in general to have models locally in devices, particularly when you have a large number of users, because it just makes it very difficult to update the model and keep track of which version of the model people have.
Okay, and one comment is that you are a little bit concerned about the sigmoid of last final layer, but actually X and sigma over X contain equivalent information, so you don't have to really evaluate sigmoid, but just send.
Yeah, so we're thinking about essentially pushing this last operation back to the client in a way. But for completeness, we implemented the whole sequence of operations. Yeah, okay. Thank you.
Well, one little note. It's not really obvious to me if it's possible to do, in the US at least, health predictions without having a publicly, published model.
I'm also not from the US, so I can't answer that.
Yeah,
and yeah, I mean, yeah.
Anyway, that's something that in all these secure computation things, not just homomorphic encryption, but all secure computation things on medical data, it might make sense for the privacy and crypto research community to make sure that we understand exactly what the legal situation is with these things.
Yeah. Yeah, and especially in a very critical case like this, where you really have patient data with Thank you.
Yep, I think just because it is really critical, make it really hard to deploy. So one thing Kim already mentioned that it's hard to keep the database growing so that you can get a better model. And the second thing is when you get a better model, how do we handle the previous predictions? Did the previous patients get worse prediction result? And what if there's inaccuracy in your prediction and you tell them something wrong? And these are just two consequences that might come after you update the model or something was wrong in the model.
Yeah, thank you.